So after we determined that light and matter had this duality, that matter could have wave properties and so forth, of course the next idea is, well, what would be the manifestation? What would a matter wave look like? And this led to the work of three very different individuals who approached this problem in three very different ways. And all, in effect, got the same answer. And so today, in this video, we're going to look at the work of Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. So with the work of de Broglie and added by the experimental confirmation by Davison and Germer and G.P. Thompson and Compton scattering and other work done in the early part of the 20s, the question then becomes, well, if matter has a wave character, what might that look like? Now, the mathematics behind all of this is way too advanced for high school, but let's just say a few words about it. So in 1925, 26, the first publication came out, and this was done by Werner Heisenberg. And his work fell out that the first contribution he made was something called the uncertainty principle. And so what we're basically suggesting here is this variable, which is the sigma, and it represents uncertainty in a variable. So we would have sigma sub x would be the uncertainty in position. And sigma sub p would be the uncertainty in momentum. Now this is really speed or velocity, because p is equal to mv, and this is constant, the mass, and so whatever uncertainty and momentum has, it'll be primarily in the velocity. And what they say is that sigma x times sigma p is greater than or equal to Planck's constant divided by 2 pi. Now how we get there and all the rest isn't important. But the main point here is to say that this was found to be a fundamental constraint of nature, that if we know the position better, then this number will be small, because our uncertainty will be less. The better we know something, the lower the uncertainty. And if this gets very precise, then this will become less so, to the extent of this. Normally the product of these two is much greater than this. This is the maximum, the minimum limit. Now remember that these are for quantum particles. We're not talking about tables and chairs and desks and people here. We're talking about particles such as electrons, protons, and small molecules and things like that. Now it may well be true for bigger things, but this is mostly something that shows up meaningfully at these small sizes. This will come back in the later part of this talk, as we'll see its implications are actually quite significant. Now Heisenberg used tables to figure things out in a complicated way, and this leads, and really in a way a parallel discovery almost, to a mathematical construct called matrices. And my understanding was that he actually even talked to Cayley about some of the mathematical implications of what he was coming up with. And so that was the first contribution to this whole logic. Now in the end, Heisenberg, Schrodinger, and Dirac all come up with a theory that describes things, and they have different aspects that show up. Okay, so let's move past Heisenberg And now we have yet another year or so. It's 26, 27 basically. And now we have the Austrian, Erwin Schrodinger. Now he used a basic form of calculus. This is the type of math that was best understood at the time, and this is what we call differential equations. There's all kinds of theory about this. Now, I'm not going to give you the equation, and I'm going to do it a little bit here. I think, let's see how we can, okay, just for a little bit of entertainment, because this is the one that we can show a little bit of. Now, I understand that this math doesn't mean very much to you. Let's first start here. So this Greek letter here is simply the Greek letter psi. And it is simply just like any other letter that you'd use to describe an equation. And just happen to use Greek ones. It's the tradition. And it's a function of time here, and position in one dimension. Now, you've seen functions of 2D before. Let's take the volume of a cylinder, for example. V is equal to pi r squared h. There are two variables here, and you could theoretically write it as V of r of h is equal to pi r squared h. So you've been acquainted with this before, and what we're saying is that this function psi is dependent upon both position and time, but this position is on a number line. This goes one direction. Okay, so let's go back here. So in this equation, these three terms here, we have this term, and it's in a notation that you probably are familiar with, but it simply says is how does psi change with respect to position? So as you move it down the number line, if you will, how does the wave function change just by its location? Okay? The other version is over here, where we say how does it change with respect to time? And this was the part that caused trouble for Schrodinger, because this I here is the square root of -1. And this meant that all the solutions of this equation were going to be complex. And Schrodinger rejected that because he felt that the equation should not be complex because it's dealing with real phenomena. Now, before I rub this out, if we look at this term here, this V, this stands for potential energy. And if we look at the equation, this is modeling, in many ways, the potentials that are holding the electron around the atom. And if there are electrons in between that electron, this potential function has to model that. And that has been a very difficult thing to do. And so this, in many ways, simply represents the central force, okay, energy in one way. So, anyhow, let's leave that for now, but this just gives you an example of how this was in part done. Now, I want to get into a little more of the problem he found with the solution. We all know that we have the real numbers, but there is a larger set of numbers called the complex numbers. And in this case, Z is equal to A plus BI, where A and B are real. So we have an imaginary part of this number, and we have a real part. So what was happening is that all the solutions to Schrodinger's equation were going to be compelled to have both imaginary and real parts. And he felt that that just couldn't be so. So what Max Born suggested was that if you take what we call the conjugate, so if you take Z equals A plus BI, and you multiply it by what we call its conjugate, you're going to get A squared, and you're going to, so let's see what happens here. If we have B times B, you're going to have negative, but I squared is negative 1, so you get A squared plus B squared, and this is equal to Z squared. And so as a consequence, and this is here Z, and this is typically where Z bar. So what this does is this is always real. So that was a good thing. But then was, what does this mean? And so by looking at what they already understood, then the implication of this is that it was the probability of the electron's location. And we could do this, and that was certainly one. And this, of course, is in effect the uncertainty principle coming out of the differential equation. Now we're going to come back to this example, this approach in a minute, but we're going to just say a little more about this. Because out of these differential equations, and I won't get into the details of the solution because it's not helpful to us, was his prediction of spin. So we have we have Heisenberg, let's just do it this way. We have the uncertainty principle. Then we have a Schrodinger. And here we have the notion of spin and in effect fine structure coming out of his work. And if you will, the orbital concept. Because if you solve his equations, you actually get the orbital shapes. Now this, of course, has to be done in 3D, but anyhow. And finally, we have Paul Dirac, a brilliant British mathematician. And he used a different type of calculus to solve the problems, which we don't need to get into. But he predicted all of the above. But he made an important prediction. His also produced prediction for antimatter. And this preceded the discovery of the anti-electron, which we call the positron, by about 6 months. The research, in addition to the theory that we've been talking about, was the first, in the late 1920s into the 30s, was the first time we were beginning to get particle accelerators and the devices that could detect subatomic particles and their energy and their circumstance in the most crude ways, of course. And so we were beginning to find that we had objects that had the mass of an electron, but actually were had a positive charge. So the discovery and the theory was coming in kind of lockstep. All three of these men won the Nobel Prize for their work, which is quite appropriate. And as we moved from the 1920s into the 1930s, a lot of the research started to move towards the nucleus. We discovered the proton, not the proton, pardon me, the neutron. the antiproton, various types of radiation, and finally, of course, nuclear fission. And all this led to work done in the 1930s, both in Germany, Italy, and in the United States. And of course, this all led up to events that followed in World War II. Now there you have 3 different ways, and obviously here we are in this non-mathematical treatment of this. We see tables of values, which you could argue are turned into matrices. We have good old-fashioned differential equations, calculus as we know it, and then a fancier version of calculus used by Dirac called the Hamiltonian, and in all cases they reveal aspects of this, with Dirac's work probably being seen as the most complete version of it all. And so at this age and development of your mathematics, obviously we're not going to be able to take these equations apart and show you in detail what they mean, but we can present them to you at least and make you aware of where it goes and give you a suggestion of what they at least implied about the world around us. Thank you so much for watching.